Okay, I think we're ready to go. Mark, do you want to take over?
Yes, thank you very much, Michele. So good morning to those of you in the US and good afternoon in Europe. Welcome to this ISBA webinar organized by Bayesian Analysis. So today we've got two truly wonderful speakers, and I'm glad to say both have a very strong connection with my own institution, which is the University of Warwick. Now, I can assure you this is not my doing, as the paper was chosen by Michele, so I'm totally innocent of this. But let me very briefly say two words about each of them. So Giacomo Zanella has successfully finished his PhD at Warwick in 2015. He received the John Copus Award, which is a Warwick Award, and also an honorable mention for the Savage Award for his dissertation. And he's now an assistant professor at Bocconi University in Milano, and is, I think I can say, a rapidly rising star with already many papers in top journals. Gareth needs very little introduction. He's been at Warwick for over 15 years, I think now, and he is a world-renowned authority on computational statistics with over 200 publications in statistics and probability. He's a highly cited researcher. There's not that many of those in our midst, and has been the driving force in many leading research initiatives. Now, what they will do for us today is they will present a paper called Multilevel Linear Models, Gibbs Samplers, and Multigrid Decompositions, which will shortly appear as a discussion paper in Bayesian Analysis. So I think Michele already alluded to that. If you have questions during the seminar, please write them in the Q&A section. Afterwards, we'll have three discussions by Quan Zhou and Shuang Zhou, then a discussion by James Flegal, and then one by Jun Liu and Xiaodong Yang. Okay. Now, after the discussants, if we have time, so at least the authors will present a rejoinder, that's for sure. But if we have time after that, then we will allow for some questions, comments, and discussion from other participants. Okay. So please again use the Q&A session. If we really have time for it, we may allow for people to raise their hand if they want to talk. Okay, but we'll see how we're doing for time at the end. All right. So I think it's now up to the presenters of the paper, Gareth and Giacomo. I don't know how you want to organize it, but
so I will present. Yeah. Okay. Thanks. I will do the presentation, and Gareth will do the rejoinder.
Oh, okay. Good. Excellent.
Okay, so I'll start sharing my screen.
Yes, please.
So do you see that?
Yep.
Okay, so first of all, thanks a lot to the Bayesian Analysis editorial team for picking the paper as a discussion paper and for organizing the discussion. And thanks to everybody for joining. So as Mark said, we're going to present a paper titled Multilevel Linear Models, Gibbs Samplers, and Multigrid Decompositions. Most of the presentation will be on that, but I will also hint to other related papers in this line of research. So, okay, so the context is the one of Bayesian multilevel models. So very generally, in Bayesian modeling, we typically build joint, potentially complex models through sequences of local, simpler conditional distributions. And this is a very kind of general and broad framework, which is highly successful and very highly related to the practical use of Bayesian methods. It has many useful features, such as flexibility, interpretability of local parameters, good handling of heterogeneity by propagating in a probabilistically coherent way information through the graph, and so on. So these kind of models naturally lend themselves to coordinate-wise updating computational schemes, such as the Gibbs sampler, for example, thanks mainly either to local conjugacy or more generally to the very large degree of conditional independence, which you typically have in these models, which help also beyond conjugate cases. So in this work, we're going to study this kind of models, and in particular, we are going to seek quantitative convergence theory for Markov-Chain Monte Carlo. So the aim, broadly speaking, is to, in a sense, deepen, contribute to the theoretical understanding of Markov-Chain Monte Carlo for multi-level or hierarchical models, and in particular, to provide a theory that is quantitative enough to influence and guide the methodological implementation, so to provide methodological guidance. In this talk, specifically, we will be focusing on the Gibbs sampler, and in particular, try to exploit the interaction between the model structure, For example, the graphical structure of the model and the convergence property of the algorithm. As I said, we'll try to provide quantitative theory with methodological implications such as computational complexity statements or guidance on how to optimally implement algorithms. Again, in a sense, compared to broad literature on MCMC, in a sense, there is a very large literature on unstructured generic target distributions. So like generic guarantees for MCMC for target distributions under, say, some smoothness assumption. Here we try to be more specific on the model and more quantitative on the results. So we consider more structured data. So the overview of the talk, I will be focusing mostly on two types of models. So nested linear models, which I will use to introduce the main ideas of the paper related to multigrid decompositions, the notion of hierarchical ordering, and the application to optimal choice of reparameterization. And then I will go to cost-effect models, which are partly discussed in this paper and in another paper, joint work with Omiros Paspiliopoulos and Gareth, on cost-effect models, where I will discuss the role of sparsity and connection to random walks. Okay, so this is the roadmap. Okay, so let's start with nested linear models. Let's consider as a pedagogical example a three-level nested linear models, where you have data which are structured in a hierarchical nested way, such as students within classes within schools. And you get observations which we denote as y, I, j, k at the local level, which you model as a linear combination of some global effect mu, which may refer to, again, like global fixed effects, AI, which may refer to a school effect, and say bij, which may refer to a class effect, for example. And these effects are a priori independent. So these kind of models, as I said, naturally lend themselves to coordinate-wise updating schemes, such as Gibbs samplers, where, for example, you update mu given A and B, A given mu and B given mu and A. And these kind of schemes are computationally convenient thanks to conditional independence, because then you can do the update of the high-dimensional vectors independently for each parameter. And so in particular, you get a cost per iteration that is typically quite scalable, typically linear in the number of observations and parameter, which is, for this kind of models, good. And so the natural question is, what is the overall computational complexity? So in particular, how does the convergence behave as the, say, size of the data and the model grow? So here we will be doing theory for the fixed variance scenario. I will discuss extensions at the end. And typically, this Gibbs sampler, you should think at this as nested inside a larger sampler, where you also update the hyperparameters then. Okay, so as I said, we want to talk about total computational cost or computational complexity of the algorithm. So for an iterative algorithm, this is the product of cost per iteration and number of iterations. And in Markov-Chain Monte Carlo, the number of iterations is related to the mixing property of the algorithm. So in this work, we're going to study, in particular, the relaxation time of the algorithm, which you can define as the inverse of the spectral gap. And the way I like to think at it is as an upper bound to the relative asymptotic variance of the MCMC estimators. So in particular, for any MCMC estimator which targets a given test function h, the ratio of the asymptotic variance divided by the variance under IID sampling is upper bounded by 2 times the relaxation time. So you should think at the relaxation time as the number of iterations you need for each effective sample in stationarity. So in multi-level models, hierarchical models, we typically seek, in a sense, the gold standard would be having algorithms whose complexity is linear in both N and P, such as scaling as the maximum of N and P as both N and P grow. And since the cost per iteration is typically linear, this means that we need relaxation time or convergence times which are order 1, so which they don't grow with the size of the model. So we want a kind of dimension-free convergence, in a sense, as a gold standard. So in general, it's quite hard to study spectral gaps or convergence rate in a quantitative way. It's still hard, but can be proved under much milder assumption to prove, for example, the existence of a positive gap, so something like geometric ergodicity. This can be done in much more generality. While, as I said, computing or bounding the gap is hard. An important exception is given by Gaussian autoregressions. So if you have a Gibbs sampler targeting a Gaussian, then you can write this as an AR1 process, where you have an autoregressive matrix B, which governs the convergence property of the chain. And in particular, the gap of the transition kernel P is 1 minus the largest eigenvalue of B. So this already, in a sense, seems enough, but the issue in practice is that you typically have a very high-dimensional matrix B whose size grows with the size of the model, and so typically it's hard to extract, in general, quantitative convergence theory from just a generic formulation. So what we're going to do, we're going to exploit the structure of the model, basically to quantify how this convergence depends on the model features. So let's go back in this with this objective in mind to nested models. Let's consider a three-level model, as I said. So Yij is modeled as a combination of mu ai plus Bij. Here, the Markov chain of interest induced by the Gibbs sampler, which targets the posterior distribution, is of dimensionality 1 plus I times j, and you should think of this as large or growing. So the key idea, at the very basic level the idea is to decompose the chain into easier and independent and easier to analyze chains, in a sense, subchains. So the way we're going to do it is by exploiting the so-called multigrid decomposition. So the first remark, first, what is the multigrid decomposition? Well, we map the original parameters mu ab into the basically residuals of different level of granularity, which we denote as delta 0, delta 1, delta 2. So for each parameter, say Bij, we decompose it as the global average B bar plus B bar I minus B bar plus Bij minus B bar I. And we denote these different increments or residuals as delta 0 of B, delta 1 of Bi, delta 2 of Bij. So these are maps. And you do the same for A and mu. And then you look at the residuals at the global level, level 0 of granularity as a vector, so the red vector, and the level 1 residuals and level 2 residuals. So you get three vectors, delta 0, which is of dimensionality 3, delta 1, which is of dimensionality 2 times I, delta 2, which is of dimensionality I times j. And so the first remark, which in a sense is the first observation of this paper, is that if you look at the time-wise transformation, so if you run the Markov chain on the original space mu AB, and then you look at the time-wise transformation in the delta space, actually what you get is the following result. So if mu AB is the Markov chain generated by the Gibbs sampler, targeting the posterior, then the time-wise transformation delta 0 of t, delta 1 of t, delta 2 of t, which are obviously stochastic processes, are actually Markov chains, and they are independent. So here we have a graphical representation of the original Markov chain, which is a Gibbs sampler. So this is a graphical representation of the Gibbs sampler, where mu depends on the previous values of A and B, A depends on mu and last values of mu and B, B depends on the last values of A and mu. And if you run the chain with this dependence and you map into the delta space, then you get three independent chains, each of which is a Gibbs sampler. So the delta 0 chain will be a 3-block Gibbs sampler, the delta 1 a 2-block Gibbs sampler, the delta 2 a single-block Gibbs sampler. So this independence is very convenient because then it means that the relaxation time of the Gibbs sampler, being a collection of three independent chains, is just the slowest of the chain, is the worst case relaxation time. So it's the maximum between the relaxation time of delta 0, delta 1, and delta 2. Okay. So a remark here is that obviously the orthogonality, the independence of the delta 0, delta 1, delta 2 residuals is well known in the literature, is a very standard and classical fact. What is not obvious, and in a sense is a bit surprising in general thinking in the MCMC literature, is that actually this independence in the target induces an independent evolution of the Markov chains. So in general, this is not true. And typically when you have independence of some components in the target, then they are coupled, the revolution in the Markov chain is coupled. And this actually, it's also not true in general, not even for Gibbs samplers on Gaussians. So for example, if you consider a simple bivariate Gibbs sampler, simple bivariate Gaussian with correlation rho, and you orthogonalize it, so you consider x and z equal y minus rho x, then actually if you take the time-wise transformation, x of t and z of t, of the Gibbs sampler in the original coordinate xy, this does not induce two independent chains. Actually, the evolution, the coupled evolution of the chain induces dependence between x and z. Here, I'm just plotting a cross correlation. So in a sense, the multigrid decomposition has more to do, I would say, with the interaction between the conditional independence among the A and the Bs and the marginal independence of the deltas, in a sense. So it's a bit of a more model feature. Okay, so the second remark, which is crucial again for this analysis, is the following: is the fact that not only these are independent chains, but actually there is in general a hierarchical ordering of the convergence rates. So in particular, if you consider the three relaxation times we discussed before, what you can show is that no matter what are the hyperparameters, so what are the values of the precisions and what is the size of the model, so the value of I, J, and K, the convergence rate of the delta 0 chain of the coarsest level residuals is always slower than the convergence of delta 1, which is always lower than the convergence of delta 2. So in a sense, you have this kind of, no matter what are the parameters, you have this hierarchical ordering, which means that coarsest level, it's always the slowest, which is something maybe not surprising to practitioners, since typically you are more likely to observe a fixed effect or higher level parameters mixing slower in practical MCMC. And the nice thing here is that since the slowest chain is the delta zero, this chain, remember, is three-dimensional. So it's just of fixed dimensionality, it's low dimensional. So it's very easy actually to analyze just by brute force linear algebra, computing the spectrum of the matrix. And you can get explicit expressions for the convergence rate and for the spectral gap and for the relaxation time, which in this case, it happens to be, for example, this expression 1 plus j times k times ratio of precisions. So for this model and this parameterization, it means that, for example, the relaxation time gets larger and larger. So the chain gets slower and slower as you increase the size of the number of parameters at level 2 and 3, so the size of j and k. And this leads in total to a superlinear cost of the algorithm, which in a sense is not scalable according to our desiderata. So apart from this specific expression, the key thing is that you can get explicit expressions. And the first application I discuss here is to the choice of optimal parameterization. So in particular, it's well known in the literature, and it goes back to a nice paper by Gelfand, Zhou, and Carlin, that if you reparameterize the model, actually you get different kind of algorithms with very different, potentially very different convergence rate. So here we discussed the Gibbs sampler on the original parameterization mu AB. But for example, if you define the so-called centered parameterization, and then this notion was extended by Papaspiliopoulos, Skold, and Roberts to more general models. So if you define the notion of centered parameterization as, for example, gamma I, which is equal to mu plus AI, and eta ij, which is equal to gamma I plus bij, then basically you are centering each parameter on the one above, meaning that you're changing the graphical structure according to the figure on the right. Each parameter depends only on the one above. It's not that they are all a priori independent and then combined through the likelihood. And this induces a different graphical model, which is again amenable to Gibbs sampling in a simple way, because again, you have all the conditional independence you need. So these two are two ways of writing the same model, which gives different algorithms. So for tree-level models, you have 4 of such parameterizations. In general, it will be 2 to the k minus 1 choice of parameterizations, depending on whether you decide to center or not each level. And again, these are 4 different algorithms for the same model. So in general, you don't want to choose a parameterization for inferential purposes, because any parameterization you use, you can do the same inference because you can map back, transform back the samples to the original parameterization. It's just about which one induces the best computational algorithm, so the fastest converging one. So, and in part, it's well known and observed in practice that this kind of difference of convergence can be very dramatic. So typically different parameterization can lead to very substantially different convergence rates. Here it's an illustrative example in the paper of 10,000 dimensionality, where you see the 4 parameterization which lead to very different behavior, and actually only one of those, according to these 3 one-dimensional projections, only one of those seems to be converging fine. And actually, it's interesting that it's not obvious to which projection to look, because if you look only at the global parameters mu, for example, here, it seems that 2 of them are converging quickly, while actually only one of them is. And here I'm just plotting 3 of the projections in a 10,000 dimensional space. So again, it's not obvious in practice how to monitor these things. So the nice thing is that, in a sense, the multigrid decomposition is not specific to a given parameterization, but is more specific, again, to the interaction between conditional independence and the residuals. So you can play the same game for all the parameterization, actually with the same set of basically spaces generated by delta 0, delta 1, delta 2. So it's more a decomposition of the model, not specific to the composition specific to the parameterization. And if you play the same game, you get the same hierarchical ordering of rates, and you get explicit expression for all the 4 parameterizations. So in this case, these are quite useful to get insight of which one can converge faster. And for example, here, I'm plotting the convergence rate, the relaxation time, as a function of the relevant hyperparameters, which in this case can be represented as a 2-dimensional space. And what you can see is that basically the 4 parameterizations partition the space in 4 regions where one and only one parameterization is mixing well. So here white means fast mixing. So basically for any value of tau, I, j, and k, you will find one and only one parameterization which is mixing well. And the choice of optimal parameterization is quite intuitive. So here we extend intuition, which was already present in the two-level models in the literature. You should basically decide whether to center a level or not, depending on whether the variance at that level is larger than the variance basically of the residual variance at the levels below. So you get some explicit conditions as a function of the hyperparameters, and you can use those to basically choose the optimal parameterization on the fly, as a function of the current value of the hyperparameters. And if you do this, you are guaranteed to have a relaxation time of the Gibbs sampler upper bounded by 3. So in particular, the gap under the optimal, conditionally optimal parameterization is lower bounded by 1/3. The relaxation time is upper bounded by 3. And this is quite, which in this case, it coincides with the number of levels. And this is quite interesting because it's independent of dimensionality. So if you use the optimal parameterization, out of the 4, actually you get a convergence which is dimension independent, which is what we wanted. So again, and this is very much a natural extension of results in the literature on 2-level models again. So, so there are much more, in a sense, more details in the paper. Here I use the 3-level hierarchical model, which is, if you want, as an illustrative and pedagogical example. In the paper, we derive basically analogous results for general and arbitrary tree structures, where we define averaging operators which are required to define the residuals using basically a random walk through the tree where the transition probability depends on the strength of correlation. And given that, you can define the residuals and derive a multigrid decomposition in general. And under some assumptions, such as, for example, centered parameterization, you can derive a generic hierarchical ordering of the rates, for example, using the Cauchy interlacing theorem, because it boils down to comparing nested matrices of varying dimensionality. So you use the interlacing of the eigenvalues to prove the ordering of the rates. So I don't go into the details there because it's a bit more technical. And I want to spend a bit more time on the other class of models I wanted to talk about, which is the one of cost effects. So here in cost effect models, we have data which do not sit in a nested structure like on a tree, but they sit on a matrix, or more generally a tensor. And so, for example, you have data Yij, which are modeled as a combination of some fixed effect, global effect mu, plus a row effect Ai, and a column effect Bj. So you have this kind of crossed model structure. Again, effects are a priori independent and combined through the likelihood. So you can think for intuition as a paradigm at recommender systems where each row denotes an item, which rates users, which sits on columns. This kind of crossed structure, in general, broadly speaking, are more computationally challenging than tree-like structures, because, for example, you cannot have tree-based algorithms such as belief propagation, or even sparse linear algebra typically scales quite poorly for this kind of dependent structure. And in general, the cost of, even in the conditional Gaussian case, the cost of one marginal likelihood evaluation or one block updating, it's typically at least n to the 3/2, which it's not optimal. As we discussed, we would like a linear cost and can be impractical in large-scale application. So here, on the other hand, you still have conditional independence over rows and over columns. So you can still do block updating and Gibbs sampling very cheaply at order n cost. And the natural question is, okay, how does the convergence scale as you get larger and larger models and data? So we will do theory, exploiting, again, a multigrid type decomposition. And in particular, we will be interested in theory which handles sparsity. So in particular, we want to assume that we don't observe all the data points at each combination Yj, but we observe only data points at a subset of row and column combination, which is reasonable. Say you have each user, which is rating only a few subset of the available items. And here we denote the set S as the set of basically Ij combinations where we observe a data point, meaning that we have a sparsity level for the observation pattern, which is alpha, which is the size of S divided by Ij. So we're gonna, so our theory will handle a general level of sparsity alpha, so that is nice. The assumption that we're gonna require, on the other end, it's balancedness assumption. So we're gonna require that the row sums of S over, so for each row, you have the same number of observations, and for each column, you have the same number of observations. So each user rates the same number of movies. Each movie is rated by the same number of users. So in a sense, that's the key assumption that we need to develop our theory. So it's a kind of Latin square design, if you want. And under these assumptions, for any level of sparsity alpha, what you can show is that the Markov chain generated by the Gibbs sampler, mu AB, again, if you consider time-wise transformations, in this case, you have two independent chains. One, which is, because it's basically, it's a two-level model in terms of hierarchy. One, which deals with the averages, mu A bar B bar, and one which deals with the residuals, delta A, delta B. And again, in this case, you can show that you have a hierarchical ordering, meaning that the chain of averages is always lower than the chain of residuals, despite the chain of residuals being quite involved. And this is quite nice because, again, the chain of averages is only 3-dimensional. You can compute things explicitly, and you get the relaxation time of vanilla Gibbs sampling, which in this case is of order 1 plus the maximum of this term. And you see the role of sparsity quite explicitly as the alpha term, meaning that the sparser your design, the faster the convergence of the algorithm. So this might be good or not, depending on your application. And in general, this means that the relaxation time is of order maximum between number of observations per row and observation per column, which can still be very large. So in a sense, this is not satisfactory. And for full designs, which is the worst case, this means a convergence time, a relaxation time of at least square root of n. And when you combine this with computational cost, this is at least n to the 3/2, which more or less matches the cost of sparse linear algebra or exact updating. So in a sense, it's not, if you use this, it's not convenient in a sense to do coordinate-wise updating. At least if you have a Gaussian model or if you do Laplace approximation in non-Gaussian models. The nice thing is that you can extend this result to k-factor models. And in this case, again, you get 2 independent chains. One is the chain of the averages, mu and a bars, and one is the chain of the residuals, which are k+1 blocks and k blocks. Again, you can play the same role, and in this case, you get a relaxation time, which is almost linear. So in a sense, the more factors in the model, the harder computationally the model is. So in this case, you get an almost linear convergence time, which leads to an almost linear computational cost overall, which is a computational cost of 2 minus 1 over k, which as you increase k, so in case k equal 2, it's n to the 3/2, as we discussed before. As you increase the number of factors, it goes up to quadratic, which can be very impractical. So we would like to solve the problem and get a dimension-independent convergence, an algorithm with dimension-independent convergence. So what about parameterizations? So these work very well in nested cases. Can we use them in crossed models? Well, you could just use them in a sense. You could center each row effect on the global effect or each column effect on the global effect, defining new parameters gamma and eta. And if you use the multigrid analysis to analyze them, you get that the convergence of those is not order 1. So it grows with the number of rows or number of items. So if you have a matrix which is large, both in terms of rows and columns, then you will get something which is super linear as a total cost, and which converges slower and slower as you get a larger matrix. And in this case, centering both, it doesn't make much sense. So you could theoretically do it, but you will get actually an even worse performance. So the key message here is that reparameterizations are not well suited to cross structures because you don't have this nesting, which is very convenient to basically reparameterize models in a centered way. So which methodological trick could we instead use in this case? Well, if we go down to the geometrical intuition, if we go back to the geometrical intuition of the slow mixing, in this case, we have typically in cross models, we have typically a negative correlation structure because you have in some sense a non-centered parameterization. So parameters are independent a priori, mu a, b, and then they are combined through the likelihood. So typically the likelihood will induce a constraint on the parameters, which will create dependence. And this kind of dependence typically lead to this negative correlation dependence. When you increase one, you want to decrease the other, meaning that the posterior concentrates on a manifold, on a subspace of codimension 1 typically. This is the opposite compared to positive correlation structure, where you have each parameter is tied to the one above and the one below. So this is a positive correlation structure where things concentrate more on a line, in a sense, geometrically speaking. So this means that, in a sense, for negatively correlated models, it's enough to integrate one block to basically restore order 1 moves and order 1 convergence. And this is crucial because in this case, we have 3 blocks, 2 of which are high dimensional, like the row effects and the column effects. So these are hard to integrate out, while it's quite easy to collapse or integrate out the fixed effects. So this intuition leads to a proposed methodology, which is a collapse Gibbs sampler, where we collapse the fixed effect mu. And this can be done without any matrix inversion. So basically, the algorithm would be every time you update some random effects, some high dimensional local effects, you update them jointly with the fixed effects. And this can be done again, thanks to conditional independence at order n cost in the Gaussian case, and can be extended to the non-Gaussian case as a methodology in a very easy way. So I refer to this paper for the extension to general likelihoods. And the key intuition is that now we have a collapsed version of the algorithm which preserves the cheap cost per iteration, and we want to understand if it improves and by how much the convergence rate. So the basic fact is that collapsing basically at a high level gets rid of the slow mixing of the averages and leaves you with the mixing of the residuals. So basically, the relaxation time of the collapse Gibbs sampler is equal to the relaxation time of the high-dimensional chain of residuals. So this is good because the chain is faster, but it's bad for theory because it's much harder to analyze because it's much higher dimension, more high-dimensional. So what can we say about the convergence rate of this delta A, delta B chain, of this residual chain? Well, so the main result there, the main intuition is that we connect the convergence properties of this residual process of the delta A, delta B chain to the convergence properties of a random walk on the conditional independence graph of the model. So in particular, we proved that the relaxation time of the delta A, delta B chain is of order the minimum between alpha J, alpha I, and this T-aux, where T-aux is the relaxation time of, again, the natural random walk on a bipartite graph with adjacency matrix S. So what it means is that you pick an item, you choose uniformly at random one of the users, you go to that, then given the user, you pick uniformly at random one of the items which rated the user, apologies, and you go to that. So you move across edges which represents observations that are shared by two parameters. So this means that whenever this conditional independence graph will have a good connectivity property, the resulting collapse Gibbs sampler will mix fast. Okay. So let's get some intuition on when this random walk converge fast or not. So to recap here, the relaxation time of Gibbs doesn't depend on the structure, on the topological structure of the graph. It doesn't depend on where the observations are. It just depends on the amount of data, on the number of observations per row, number of observations per column. The collapse Gibbs sampler instead has a relaxation time which is the minimum between number of observations per row, observation per column, and this auxiliary chain. So the intuition, in a sense here, is that this delta A, delta B chain converges through a diffusion on the graph more than through an autoregression, in a sense. So the key fact here, which is nice, in a sense, is when you increase the number of observations, the first two terms in the minimum grow, while the third term, the auxiliary relaxation time, decreases, because the more data, the more connected the graph and the faster the random walk. So if you pick the example on the left, this means that every item rates only a few users, and this kind of rating are on a banded structure for kind of visual purposes here. So it means that the random walk will have to stay within this black band and will converge very slowly, but the number of observations per row and column will be small. So when you increase the amount of data, the first two terms increase, but actually the convergence becomes faster and faster because the chain can move, is free to move in the black region. And the nice aspect is that when you have a random design, a more like a randomly scattered pattern, such as an Erdős-Rényi random graph, by missing completely at random design, these designs typically lead to very fast convergence of the associated random walk. So typically, even if you have a few observations, but the design is very unstructured, the random walk will converge very fast, and the resulting collapse Gibbs sampler will converge very fast. So there are still worst case scenarios, such as having a very strong community structure. So for example, having two communities which are completely separated. In this case, both terms, the number of observations per row and column, and the auxiliary random walk will be large. So there are still worst case scenarios where the collapse Gibbs sampler will get slower and slower. But on average case scenarios, the sampler will become faster and faster. And the way you can formalize this is by connecting to more random graph literature in the probability theory literature, which tells us that basically when you have a random graph, like an Erdős-Rényi construction, this has an almost near optimal connectivity. So these are typically called expanders. And in particular, Friedman's second largest eigenvalue theorem tells us that basically if you have a D-regular graph with D fixed, so the number of, say, ratings per item fixed, and the size of the graph becoming larger and larger, the gap is of order 1 minus 2 over square root of D. It doesn't matter here the exact expression, but the gap actually doesn't go to 0. So it means that the relaxation time of the auxiliary random walk on a random graph actually remains order 1, regardless of the value of D when n goes to infinity. So these results can be extended in the literature, are extended to bipartite graphs, which are what we care. So in a sense, the corollary here, which is quite informal, so we're formalizing that, is that the collapse Gibbs sampler mixes fast for crossed models with average designs. So you can formalize the intuition that if you have a missing at random design or an Erdős-Rényi design, then the convergence rate of the associated collapse Gibbs sampler will be small regardless of the ratio between number of parameters and data. So here, just one remark is that this is very much, so this is quite interesting in a sense at a high level, and is very much the opposite picture compared to sparse inner algebra, which performs very well when you have a structured design. So in the example of before, banded designs are ideal for sparse inner algebra, but they're actually worst case for something like a collapsed Gibbs, while unstructured random designs are in a sense worst case for sparse inner algebra, but best case for coordinate-wise updating schemes like the one we're studying here. So it's kind of at an high level, it's quite an interesting comparison, I would say. Okay, so just before concluding, I'll just show you some simulations. So here we provide some simulated data for fixed precisions at the moment, where we can compute the relaxation times numerically and compare with the predictions given by the theory under balanced levels. And here, the key point here is that you see that the Gibbs sampler, as you increase the number of data points, has a relaxation time which grows and grows. So this means an algorithm which not only increases in cost per iteration, but it also mixes slower and slower. And that's something we don't want to get a scalable algorithm, while using collapsing, in this case, gets an algorithm whose relaxation time is uniformly bounded and actually increases with the size of dimensionality. So for high dimensional metrics, crossed models with high dimensional matrices, you have this kind of almost independence in the limit. So here, an example with unknown precisions where you update also the precisions. So this is the realistic model you would fit. We compare the vanilla Gibbs sampler with the collapsed one and with Hamilton and Monte Carlo as implemented in the default version, it's done. So here what you get is that both Gibbs sampler have a cheap cost per iteration, thanks to condition independence. HMC here has a larger cost per iteration because it requires many leapfrog integration steps per iteration because the dimension is large, it's 4,000 dimensional. And so overall, the only algorithm which combines cheap cost per iteration and fast mixing is the collapsed Gibbs sampler in this example. And for this example, LME4 package, just for reference, took around 40 seconds. And so in a sense, we are matching more or less the runtime of frequentist software for this kind of problem. Two examples, which again, I go through very quickly. In the paper, we discuss a Poisson regression example, where actually here we use multigrid decomposition to quantify the computational implication of having identifiability constraints, which is another way to speed up the sampling in these problems. And it's quite interesting that the same intuition that you get for Gibbs extends to, say, HMC. So typically, if a reparameterization or an identifiability constraint is good for Gibbs sampling, which is a bit easier to do theory, it can be good also, it tends to be good also for other schemes, such as Hamilton and Monte Carlo. So in a sense, those results are also useful potentially to guide implementation of those. And finally, you can extend the methodology and not yet the theory to cases where you have you don't have conditional conjugacy, so you don't do exact Gibbs sampling, but you do metropolis within Gibbs. Okay, so we would like to do theory also there. We haven't done it yet. But you can easily extend, in a sense, the methodology. You can do a metropolis within Gibbs scheme, which approximates the ideal Gibbs sampler in a sense, and you can get good empirical performances. So there is, not sure how much time I still have, but in the last, say, 1-2 minutes, there is some related ongoing work in this line of research that we've been doing. One is to provide a rigorous analysis of the full model with unknown variances, and we're doing this jointly with Filippo Ascolani. And then also another interesting line of research, in my opinion, is to exploit multigrid type analysis and methodological improvements for variational methods, for example, mixed effect models or structured hierarchical models. And finally, we're also applying the same kind of idea and collapsing tricks to probabilistic metric factorization. So to conclude, in this work, and specifically in the two papers I'm going to mention later, we propose a multigrid approach to analyze Gibbs samplers for multi-level linear models. So this allows to provide explicit convergence rate and complexity statements, which lead to quantitative methodological guidance. For example, on how to center parameters, how to collapse, or how to put identifiability constraints. And specifically, it gives an order n sampler for cost effect models, which is something not easy to achieve with other methodologies. And finally, more at a theoretical level, it highlights a neat connection between MCMC convergence behavior and the graphical structure of the model through the random walk, which would be very interesting to explore more theoretically. In a sense, as a take-home message, I would say that for large hierarchical models, you can achieve linear complexity, but you need to exploit the structure of the model in a sense, especially appropriate conditional independence, I would say. The main reference, so for this talk, the main two papers are obviously the discussion paper, and also the cost part is developed in the joint work with Omiros and Gareth on cost effect models. And thanks for listening.
All right, thank you, Giacomo, for a very interesting and also very well-timed presentation. Very good. So we have a number of sort of invited discussions, and I'd like to give the floor to those now. The first one is by Quan Zhou and Shuang Zhou. I thought I saw Shuang in here.
Yes, so I will do the presentation.
Oh, you'll do it. Okay, fantastic. Good. So can you share your slides? Yes. Fantastic, yeah. Wonderful, thank you.
Thank you very much. So congratulations to the authors for a very stimulating paper, and many thanks to Michele, Mark, and Tommaso for organizing this fantastic webinar. We are very happy to be part of it. So I wrote up this discussion with my collaborator, Zhou, who is currently an assistant professor at Arizona State University. So I would like to first briefly discuss the multigrid decomposition method Giacomo and Gareth developed in their paper from a slightly more general perspective. So Giacomo has already mentioned this result in his talk. So this is theorem 1 in the seminal work of Gareth Roberts and Zhou in 1997. So this theorem gives us the convergence rate of a Gibbs sampler targeting a multivariate normal distribution. And the convergence rate is just given by the spectral radius of matrix B. And here I'm just using this beta to denote this normal random vector with mean mu and the covariance matrix sigma. So this B, well, actually in the paper of Roberts and Zhou, we call it a B matrix. So the expression for this B matrix is actually pretty complicated. We need to first calculate something that is called an A matrix, and then we can calculate the B matrix using the A matrix. However, the most important thing here is that to calculate the B matrix, all we need to know is just the precision matrix of the target multivariate normal distribution and our blocking strategy. So how we are going to partition the coordinates of this multivariate normal random vector. So for a Gaussian statistical model, once we specify the values of all the various parameters, then we can calculate this precision matrix, and then we can calculate the spectral radius, and we get the convergence rate of the Gibbs sampler. Of course, to make this powerful result useful in practice, then we need to be able to evaluate the spectral radius of the matrix B. And in reality, I mean, the problem here is that the dimension of the B is the same as the dimension of the target normal distribution. So it can be very large for some problems. And we know that, well, calculating the spectral radius has cubic time complexity in the matrix dimension. So how we are going to say calculate this spectral radius, and ideally, I think that maybe we would wish, say, we can find some matrix, let's say big data, that can diagonalize or maybe block diagonalize this matrix B, and then finding the eigenvalues of the matrix B would be a lot easier. So one main result of Giacomo's paper, which we found really impressive, is that, well, Giacomo and Gareth, they showed that for a large class of Gaussian hierarchical models, we can actually use this technique, which we call multigrid decomposition, to construct, say, this matrix big data, such that, well, delta B delta inverse becomes block diagonal. And more importantly, the eigenvalues of every individual diagonal block of this matrix can be evaluated very easily. Well, so for example, this is how we construct the matrix data for the hierarchical 3-level model given discussed in Giacomo's paper. And we can to find the eigenvalues, we actually only need to evaluate. We actually only need to numerically compute the eigenvalues of a 3x3 matrix for such a 3-level symmetrical model. So this is I mean, this is very impressive because we have dramatically reduced the complexity of finding the spectral radius. And I think another way to look at this result is to imagine that, well, we are just performing a linear transformation of the random vector beta. So instead of looking at the original random vector beta and this Markov chain, this Markov chain corresponding to the Gibbs sampler, say beta S, now we are looking at the new Markov chain, say delta beta S. And this new Markov chain delta beta S, again, it's just a multivariate normal AR1 process, and its convergence rate is actually just the same as the convergence rate of the original chain. So of course we can choose to work with whichever is more convenient. So I'm just rephrasing the multigrid decomposition result developed in Giacomo's paper. Well, using a slightly different notation. So here, this big delta is a matrix. I just use it to replace the little delta operators defined in Giacomo's paper and also in his slides. Okay. So next, I would like to, next we performed some numerical experiments for the two-level linear mixed model. So this model was not discussed in Giacomo's paper, but it is actually popular. It is actually very popular in the Gibbs sampling literature. So for simplicity, we only consider the two-level case where the mean of the group I is given by mu plus xi transpose alpha plus beta I. And here xi is just a vector of observed covariates. And mu, alpha, beta, they are unknown parameters. So if we impose, say, a normal prior on all the parameters and assume the error follows a Gaussian distribution, then the joint distribution of the parameters becomes normally distributed, and then we can, and once we specify the variance parameters, we can write down the B matrix, and we can calculate the spectral radius of the B matrix, and we can find the convergence rate of the corresponding Gibbs sampler. So here are some numerical results for the values of this rho B under three different parameterizations for this two-level linear mixed model. And here we have considered the centered parameterization, partially non-centered parameterization, and a non-centered parameterization. So essentially what we have observed is the same as Giacomo has discussed in his paper. So we calculated these the spectral radius of B under three different settings of the various parameters. And we found that when the error variance, say sigma E square, when the error variance is really large, which means that when the data is not informative about the model parameters, then probably the best choice is the non-centered parameterization. And if the data is very informative about the model parameters, then probably we want to use the centered parameterization. So of course, this is consistent with what was observed in Giacomo's paper. And I guess this suggests that the statistical insights obtained in Giacomo's paper can probably be applied to a much more general context. Okay. And to sum up, finally, I just want to make a couple of more remarks. So in Giacomo's paper, I think Giacomo and Gareth, they are essentially imposing some assumptions on the precision matrix Q. So they assume that the precision matrix of this target multivariate normal distribution factorizes according to the tree, and this tree needs to satisfy some needs to satisfy some symmetric conditions. So I think it will be interesting to investigate whether we can somehow relax, say, these assumptions. For example, can we assume the precision matrix factorizes over a decomposable graph and still apply, say, this idea of multigrid decomposition in some way? And the last thing I want to comment on is that, well, I guess one main takeaway from Giacomo's paper is that when we run an MSMC algorithm on a high-dimensional space, we need to care about, say, in which directions the chain is mixing most slowly. And if we can somehow predict these directions, then we can do something to improve the mixing behavior. So I guess that this general idea is kind of popular in some other MSMC methods, and it would be very interesting to study whether we can somehow utilize this idea in a more general setting. For example, if we know very little about the target posterior distribution, then can we somehow learn, say, these directions in which the chain is mixing slowly during MSMC sampling? In other words, can we somehow learn the optimal parameterization as we are running an MSMC sampler? So perhaps this is another possible, say, interesting direction for future research. So that's all for our discussion. Thank you very much.
Thank you, Quan. That's very very informative and again, so quite well timed. So our second discussion is by James Flegal. Is James around?
Oh, I'm here.
Yes.
Can
Good.
you hear me now?
Yes. I can hear you. We can see your slides, so wonderful. So just go ahead.
Perfect. All right, so I'm going to talk about a fairly narrow aspect of this and really more a practical aspect where thinking about, looking at reparameterizations in a less theoretical and more practical manner in regard to MCMC output analysis. But before I move into that, I really want to just highlight the fact that, when we're doing an MCMC simulation, this really is finding that mixer or finding that sampler that mixes well is almost the most challenging and the most important part of the process. So, this work is very, very exciting, and I really appreciate Giacomo and Gareth for developing this theoretical framework. And I'm even more excited about, how quickly it drove this very robust discussion, given the extensive contributions to this discussion paper. So, I'm thankful to Bayesian Analysis for selecting this as a discussion paper, and also just the involvement with the community in problems like this, because I find these to be very, very interesting problems. The model that I'm specifically going to talk about is what's referred to as model S3 in the paper. It's this symmetric 3-level Gaussian linear model where it is sort of the firm example for where this multi-grid decomposition takes place. So it's the standard specification that's in the paper. But I'm going to look at it from, again, more of an applied perspective. So I'm going to look at simulation. So I chose some parameters here. My I, J, and K match with, and mu match with what is presented in the paper. And then I played around with a variety of different variance components here. Naturally, we can use the results to then calculate the rates of convergence on the different Gibbs samplers. For simplicity, I kind of played with these rates to a point where, I chose the fully centered parameterization in blue as the best option, in the one that mixes the fastest, and then the fully non-centered parameterization in red as sort of the worst option. Just from a presentation standpoint, these were selected really just because they're a little bit more easily interpretable about what we mean by a fully centered and fully non-centered parameterization. So theoretically speaking, in this setting, we know exactly which one we should use. We should choose the centered parameterization, and that's clear when I look at a trace plot on the next slide. But the number one or the primary output analysis challenge is the fact that in this model specification, we have over 10,000 parameters. And so, as Giacomo mentioned in his talk just a couple minutes ago, that one of the real practical challenges here is how to monitor convergence. And so what's done in the paper, and I think what is a very natural thing to think about, is to look at averaging over the parameters. So we're looking at sort of, in this non-centered parameterization, this is the slow one, the non-centered parameterization. This is the fully centered parameterization, the fastest option. We're averaging over these different levels. So that's what A bar, B bar represent. It's reparameterized to gamma and A to here. Now, naturally, we have fast mixing, but notice we're only looking at trace plots from 3 of over 10,000 parameters. Now, everything looks great on this side, and we expect it to look great given the theoretical guarantees that we have for this model. But in practice, we might not have those theoretical guarantees. So what are some options here? Because we certainly can't monitor 10,000 trace plots simultaneously, or even a couple hundred trace plots simultaneously. So in short, it's sort of unclear that, and I don't have a firm answer, but it's unclear that looking at these global means is sufficient to monitor convergence. What we really want is some guidance in terms of helping to determine a subset of parameters that we can use to monitor convergence, so that we can dig deeper in that subset of parameters. So what I've offered as a potential solution, I say potential because it's definitely more of an empirical solution, is to just look at effective sample size plots or histograms for those 10,000 parameters, And I'll show those on my next slide in terms of how they interact. But I want to highlight, and I'll highlight on those histograms, is that when we do these reparameterizations, we're almost guaranteed to change these estimates of effective sample size and even the interaction between these. So the relationship here is in no way linear and in no way simple. And effectively, it has to do with, it's not based strictly on, I mean, I'm looking at univariate effective sample sizes here, and it's not based strictly, when we do the reparameterization, there's a correlation between the parameters, the original parameterization, and the new parameterization that we're not accounting for here. That's a very complex relationship that does impact these effective sample sizes. So on the left, I have the non-centered parameterization. This is sort of the slow mixing version. This is the one we might want to avoid. On the right, I have the fully centered parameterization. This is the fast mixing version. This is the one that we might be most interested in. And I think the empirical thing that stands out from this, so what are these plots? These are histograms of the different, based on 5,000 draws of the different parameters in here. So essentially I have these are effective sample sizes for every parameter associated with A, and then it's the global mean is highlighted as a red spike. So what I see is my effective sample size for my A parameters is actually conservatively estimated by looking at the global average of those parameters, the global mean of the A parameters. Again, this is sort of the slowest mixing component in those trace plots. Or the slowest mixing component is this global mean for A. This is the one we want to avoid. And what I'm doing, and when I choose that global mean, is I'm ending up with a very conservative estimate with regard to effective sample size. So from monitoring convergence, I'm actually very safe here. The same is true for these very fast mixing components related to to B and to the eta parameters at that lower level. And so in sort of 3 of these 4 cases, looking at the global mean of these parameters is actually pushing my analysis or my monitoring of convergence via effective sample size to be quite conservative. However, that's not universal. In this case, which is my sort of, this is the best case scenario, and this is the slowest mixing component of the best case scenario, these gamma parameters. I don't see that behavior. I see, looking at the global mean is sort of, it's giving me a representative behavior of all of those. And look, I don't want to highlight that this is alarming, because I don't think it is. My global mean actually is, I think, very representative of all the other parameters. It's just, it's interesting that it doesn't follow the same behavior as other pieces. And so the thing I would highlight, though, is that these type of analysis, these type of empirical calculations can be done in a matter of seconds or less than a second in these cases, and they do provide us some very nice informative information of, okay, given these high dimensional spaces, how can I look for what I might want to monitor much more carefully in terms of trace plots and autocorrelation plots, and even sort of different, even outputting, hey, I think the chain is behaving well at this point. All right, so I want to just conclude with again, thank you for Giacomo and Gareth for this notable paper, and for all of the fellow discussions and their interesting contributions here. I'd also want to thank the opportunity to speak here, Michele, who invited me to participate, and for organizing this discussion webinar.
All right, thank you very much, James. That's again well timed and extremely interesting. So we have one more discussion to go, which is the discussion by Xiaodong Yang and Jun Liu.
Okay, I will start. So you see the screen well.
Mm-hmm.
Okay, so first I'd like to thank Giacomo and Gareth for this wonderful work, really stimulating, and a lot of things to digest. And also thank Michael for inviting us to discuss That's really a sweet experience. Bring me back a lot of wonderful memories, like the first time I met Gareth many years ago, and so it's great. At that time we were just starting to learn about deep sampling and doing some papers. It's great. It's quite a few years ago. Anyway, as I mentioned, there are quite something to discuss, but we will focus on the relatively easier part. The cross effects part is great, especially the connection with random walks on the graphs and so on was so wonderful. So, but we are not going to venture there. It's probably a lot more to think along. Here's a quick highlights of our discussion, and I will just give a quick summary. One is a simple extension. We think it could be interesting to consider vector hierarchical models in the sense that every measurement is a vector of multiple things, like a person's different health indicators, like weight, height, blood pressure, and so on. And then it could be interesting to study how the rates changes in this case. Initially, we thought it's relatively trivial to generalize, which probably partly is true. But once you consider non-diagonal covariance matrices, like I indicated here, then they become more complicated. But even when they are diagonal matrices, there are some variations that's interesting. Another aspect is the how we consider this or generalize this multigrid decomposition ideas into more general settings, including covariance or even more general linear regression models. As Quan mentioned in his discussion, that it's just like a transformation of the parameters. So conceptually, you can always transform to make the after transformation, they're all independent in regression, but that's probably not what we want to do. That's becoming less meaningful. But where we should stop and how we should do that, that's a question. I will leave more details to my collaborator. And the last part is a little investigation of how this partial sampling can be integrated into this framework to bring more variations in terms of reparameterization. So I'll leave the detail to my wonderful collaborator, Xiaodong Yang. And I'm very glad to know him through this work as he is an undergrad student in China and doing some summer intern with me. So it's so Xiaodong, you will take over from here.
Okay, I can start to share my screen. So can you see my screen now?
Yes.
Maybe we can start from here. I will talk about more details and some primary results. Well, firstly, let's take a look at a vector version of the simple two-level hierarchical model displayed here. The point is that every letter represents a vector of dimension L here. And we model the epsilon and A as multivariate Gaussians. But after imposing a standard prior, we will apply multigrid decomposition to the standard associated Gibbs sampler, and we can derive the convergence rate of it as rho 0. Our next contribution is that we can also turn our attention to the following centered parameterization, and we can also obtain its convergence rate. Well, rho 1 differs from rho 0 in this matrix here. Here we use the inverse of sigma A, while in the rho 0 we use J times the inverse of sigma E here. This part is the same. We have some observations. Firstly, for the scalar version of this model, we find that rho 1 and rho 0 can sum up to 1, but but rho 1 and rho 0 can be very large simultaneously for the vector version. And the second observation is that when both the sigma A and sigma E are diagonal, we can just separate the dimensions, and we can just justify the optimal component-wise parameterization. In this, we will use some index indicator C. Well, we observed that it is possible to extend our primary results to 3-level and cross-effect models, but actually it can be very challenging to understand the rules of parameterizations. Oh, well, I forget to mention that the norm we use here is the spectral norm of some L times L matrix here. So it's really challenging to understand these norms of some matrices. And our next question is that, do we have a uniform bound on the minimum of rho 1 and rho 0 relating to L? Just recall Giacomo's lecture. He said that we can have linear complexity if we have some uniform bound. So this is our question. And
right, just mention this is for non-diagonal case. In the diagonal case, you could get an optimal solution by component-wise reparameterization. But for non-diagonal case, you probably have trouble.
Yeah. So our next question is that how can structural assumptions help us accelerate the sampler? Well, by saying structural assumptions, I mean diagonal assumptions or block-wise diagonal assumptions and so on. Well, our next contribution is about incorporating covariates. Let's firstly take a look at this model. Well, this model has some similarities with the model talked by Quan before. But the difference is that we use different covariates for each individual, not each subgroup. And we set a multivariate Gaussian as a prior on beta. Well, we investigate a standard Gibbs sampler alternating from beta and A. Our finding is that when the number of covariates P is smaller than the number of subgroups I, we can obtain its convergence rate as this complicated formula. Well, X bar here is an I times P matrix, and its ith column is the mean of covariates within the ith subgroup. Well, this formula reduces to a simpler form for the original model. And we raise some more questions. Well, this result doesn't generalize well when having more complex hierarchical structures, such as, well, the 3-level structures. Yeah, here we just use a two-level hierarchical structure here. And this is a bit straightforward because of a new cross term, A times B. This cross term prevents us from using the theorem directly. And maybe we can consider a 3-way Gibbs sampler. Well, and our next question is about linear regression in this general form. We consider a sampler alternating from beta 1 and beta 2 here. Our finding is that if we have some orthogonal matrix Q, such that this equation would hold, this is kind of like a structural assumption as well. And in this case, we can have some analogous theorems to analogous multigrid decomposition. Well, our question is that is it possible to design a better Gibbs sampler for this general case? So our last contribution is about the partially centered parameterization. Here we display a 3-level model. So we introduce 3 real numbers ABC here to continuously trade off between the 4 parameterizations mentioned before. And for any real numbers ABC, these models are exactly equivalent. And for 2-level models, the standard Gibbs sampler can converge in 1 step if we choose A appropriately. And for 3-level symmetric models, we can also find suitable ABCs to have a perfect sampler. But the first obstacle we want to mention is that the suitable A or ABC is usually determined by the variances which are assumed to be known. But in real life experiments, we usually don't know the variances. And does this method apply to more complicated structured models? And the last core question is that, are the results generalizable to non-Gaussian cases in some way? Because the perfect sampling property only holds for these Gaussian cases. So this provable benefit is only holds in the Gaussian cases, and we want to know more. I guess that's perhaps all of the contents of our presentation. And thanks for your attention.
All right, thank you very much, Xiaodong and Jun, for a very interesting discussion. Now, Gareth has the perhaps not so easy task to address quite a lot of issues and questions in about 10 minutes. So, if you could go ahead with that, Gareth, the floor is yours.
Very much. I'm just finding the share screen thing. Okay. Can you see that?
Yes.
Yeah. Okay. Thank you very much. Okay. Thank you very much. It's a really great pleasure to be talking here today. Thank you very much to Michelle, Mark, and Tommaso for fantastic organisation for this meeting, and in particular, thank you very much for the to all the discussants. I mean, I think Giacomo and I have really appreciated the interest in our work very much, and many of the contributions, as you've seen, have been really substantial, and we're glad that we've gone some way to sort of stimulate some further ideas in this area. I should emphasize very much that there are also other discussions which have been submitted in writing, which were not invited discussants, which hopefully you'll have an opportunity to read in due course, and maybe some of them will come up later in questions. I can't help but reminisce briefly, as Jun did. I mean, as some of us have been trying to make progress in this area for almost 30 years, and it makes me feel really quite old saying that. But I think it's no surprise really that the sort of the massive increase in the use of Bayesian multi-level models and the development of the Gibbs sampler and MCMC happened at exactly the same time, right? I mean, and at the time it was a great mystery in the early 90s as to why the Gibbs sampler seemed to sort of work like a dream on lots of these problems. Well, usually it worked like a dream, and sometimes it didn't, and we didn't really know much about when it was working and when it wasn't. And so that's been something I've been trying to make small contributions on for many years, but I think recently, I think a number of people, like Giacomo and many of the discussants have been coming into this area and really bringing new ideas and new concepts. We're moving forward again, and it just feels really exciting to still be around to see it, I guess. So in terms of responding carefully to all the comments, I'm really going to completely fail to do that, and we will respond in writing in much more detail than I'm going to talk about now. But I will pick on some comments that have been made. Some of them actually in the discussions that were actually not presented, but I still think are sort of particularly interesting. Right. Okay. So there's a lot of discussion, and quite rightly, about the generality of these methods and their extensions. And I think this is a really important point. Of course, our methods are limited to Gaussians, or at least conditionally Gaussians. And there is some limited theory. I have a paper with Sujit Sahu, I think is actually on the webinar, of basically showing that in the large data limit, then many hierarchical models behave as if they're Gaussian, and therefore a lot of the results can kind of carry over in some asymptotic sense. But there's a lot of work still to be done in this area to make those results stronger and to somehow kind of quantify, you know, when you get to the kind of a Gaussian domain. And these are kind of hard questions. A number of people asked about random scan samplers. We haven't concentrated at all on random scan samplers in the paper, but really I think these are important, and you know, sometimes mixing can be very different, can be better or worse for random scan samplers. But a lot of the same principles that we've applied in this paper could be extended in that direction, and that's something would be great for some people to look at. Also, I mean, in the discussions, there's really very sort of kind of you know, rich extensions to other areas, spatial models, regression models, and other areas which I don't have time to go into in detail here. Yeah, so a number of people asked about extending the theory directly beyond the Gaussian case, and I think this is really very hard, and I think it would require some really sort of new breakthrough ideas. It would be great to be able to do some of these things. I mean, some of the sort of theory does extend, but it doesn't extend to the extent of being able to give you explicit results. I will say something later about weaker qualitative convergence results that you can make, which are kind of closely related to ideas in the Gaussian case. And we really appreciated Zhou and Zhu's really elegant matrix formulations of the theory, and maybe this will be one way to lead to substantial generalizations of our work, which hitherto we haven't thought of. And finally, I mean, I think, you know, we've been working on the Gibbs sample. The Gibbs sample is a very specific algorithm, but there are lots of algorithms that have very similar structures and very similar behaviors, particularly on Gaussian and close to Gaussian distributions. They asked in particular about coordinate ascent variational inference. It's a really great question, and it's ongoing work of Giacomo's with Omeros. But there's also other algorithms that fit into this. You know, for instance, the popular conditional maximization EM algorithm. Sujit and I have a paper going back to 1999 in which we basically show that exactly the same convergence theory that you use for the Gibbs sampler can be extended to that context. And so all the same reparameterization ideas and conclusions and non-centering and centering and all that kind of stuff, it all translates over to that context. So yes, we shouldn't forget about this. And it's all a consequence really of the properties of the Gaussian, you know, that the mean and the mode are the same thing. So when you're doing maximization and taking expectations, you're kind of doing the same thing. So the matrices that describe everything are the same in these kind of different problems. So there's some exciting new areas, directions there as well. So I want to mention two things. So a number of people talked about the conditionally optimal parameterizations, and this is in some sense a very simple idea. You know, as Giacomo showed in the simple S3 model. You know, if you want to optimize your update for beta, then it's going to be different, the strategy you want to use, depending on the variance components, okay? And, you know, the results in the paper tell you exactly what you should do in terms of the various components. So in principle, you can just change those various components on the fly, and you can implement this with no significant costs. But there were some concerns that this might actually introduce some kind of bias. It's a kind of adaptive MCMC strategy, because I'm basically changing my MCMC algorithm on the basis of what the current state is. But there's actually, you know, very simple general result on MCMC, not even just MCMC, just general Markov chains really, that says that this is all okay. And I just formulated it here. That, you know, if you've got a distribution on two components, beta and sigma, any distribution at all, and suppose you have a family of Markov chain kernels, which basically leave pi invariant by only changing beta and do not change sigma. Okay, so sigma is actually fixed in terms of this. But then basically what you can do is you can always set lambda, a strategy for lambda as a function of sigma, which picks a particular lambda on the basis of the current value of sigma. Then p lambda sigma is also invariant for pi. So this is a general strategy that you can always use without worrying about the sort of complications that adaptive MCMC issues come up. Okay, the other thing I wanted to say was something about the K-level results, which Giacomo didn't have too much time to ask about, but there were some very nice comments by Sam Power and Andy Wang about the results in section 7 of the paper. And in particular, I'm going to put up corollary 7 of our paper, which is this result here. I don't have much time to go into really what's going on here, but this is the matrix that you get for the SK model. So we have, you know, the complete symmetry model here. What is this really doing? It's basically a K row a model. The terms in here are all determined explicitly in terms of the number of parents of every component and also the precisions at every level, these tors. Okay, so we get this matrix MK. So what's really going on here? Well, what's really going on here is if you want to update this parameter S at level L, which has parents PAS, and suppose C bar is the mean of its children, then essentially the full conditional distribution for S, conditional on everything else, is really just going to be weighing up the influences of its children, which is the C bar component, and its parents, which is the PA component. Okay, and the relative weights that you're giving to these two aspects, the children or the parents, is given by the elements of this R matrix. Okay, either the R from the RLS or one minus RLS. Okay, so this RI is determining the relative influences of these parents and children. So the mixing of a Gibbs sampler clearly depends on this kind of local dependence in the full conditional being propagated throughout the whole model, and therefore, so the iterative powers of this matrix are going to describe this precisely. And of course, we can actually calculate the principal eigenvalue of this, the Perron-Frobenius eigenvalue, because it's a non-negative matrix, and this describes the asymptotic geometric decay of its elements. But what I wanted to highlight was something which we don't have in the paper, which is a probabilistic analysis, which I think is quite nice. If we look at this, then this matrix MK is a substochastic matrix. It's a stochastic matrix in the middle, but when it gets to the levels 1 or k minus 1, either the top or the bottom, then it has probabilities which sum to something that's less than or equal to 1. So it's substochastic. And so suppose we have a substochastic, a defective Markov chain Y, which has the property that it essentially can just disappear when it gets to 1 or k minus 1. Well, the analysis of this kind of Markov chain is a kind of classical area of probability Markov chains called quasi-stationarity. And in fact, the principal eigenvalue can be characterized in terms of how quickly or the probability of staying within this region without exiting decays. So you have the equation at the bottom there that log rho is basically the limit of the log of the probability of tor being bigger than n over n, where tor is the first exit time from 1 to k minus 1. So there's a whole host of quasi-stationary results which can be used to basically analyze this and make some kind of analogies. But we can say some fairly simple things here. So for instance, if the exit probabilities either at the top or at the bottom are small or are large, that's going to mean that it's difficult to exit, and therefore the probability will be small. and vice versa. If those probabilities are larger, the probability of exiting are larger, then these probabilities will then rho will actually decay more rapidly. So there's a lot of comparison results that you can get for free out of this, which are not very well explored as so far. So two obvious things we can say are the following. Rho is monotonically increasing in tau 0. In other words, this is saying that, you know, in the flat prior case, that is the one that we're very often thinking about here, where we have precision at the root level, tau 0 equals 0, is the slowest Markov chain, and everything else is quicker than that. So if you can analyze that, then that's the worst case scenario, and everything else is better. And another thing we can say, and I don't have time to go into the details of this, but if tau 0 equals 0 in this vague prior case, rho is actually monotonically decreasing as a function of IL for each L, of the number of leaves for every node. And in particular, the more data that you get, the faster your convergence. Okay, and this follows just by some simple probabilistic comparison for this Markov chain, Y, saying that it basically leaves more rapidly or more slowly, depending on the choices of various aspects. So there's a lot of things that we could say more about that, which are sort of, I think, at the moment underexplored. Okay, so outside the Gaussian case, you can do interesting things which are related to this. This MK matrix, one of the characteristic features, of course, of Gaussian distributions, if you look at the precision matrix, it's constant. It doesn't depend on where you are in the state space. But outside the Gaussian case, we can actually look at notions that are essentially asymptotic MK matrices. And by looking at the behavior and the quasi-stationary behavior of those asymptotic matrices, we can characterize convergence in a qualitative sense, at least, geometric and uniform ergodicity, which I think were alluded to very briefly in Giacomo's presentation earlier. So much more that could be said from these kind of angles as well. Okay, just to finish, because I'm sure I've gone over time, we are really delighted and for all the interest in this work. And I think, you know, the idea of linking the structure that we have in very, very common classes of models that we're using day in, day out as Bayesian statisticians, and linking that to convergence is a powerful idea, and hopefully it still has an awful lot to go. And hopefully our paper's gone some way to sort of stimulating some more work in that area. Of course, we've at the moment only got rigorous results for the Gaussian case, and there's a lot of interesting developments that we could have in the direction on Gaussian cases. A lot of our ideas at least extend to guidelines in the non-Gaussian models. Of course, we don't have ultimate guarantees yet about any of these things. And finally, many thanks to everyone for contributing, everyone who's attending and is still online. We're very grateful for your interest and support. Thank you very much.
Thank you, Gareth. That was quite a task indeed. So good, excellent. So we are sort of running close to the time that we should really shut this down. But we had, I think, in the chat we had one question about GLMs. If either Gareth or Giacomo wants to say something about that in a minute or so. Alternatively, we can ask if anyone else has any questions or comments that are burning.
Gareth, do you want?
Time. Yes.
Gareth, do you want to answer that, or like?
Yeah. So well, we can both have a go if you like. Yeah. Thank you for the question. Okay, GLM. Okay, so outside the Gaussian, we talked a lot about extensions to the Gaussian case, and many GLMM contexts look approximately Gaussian, depending on data and depending on this particular structure. So our work can actually give guidelines in that situation, but in terms of theory, we don't currently have anything. Of course, it would be wonderful to be able to develop theory outside for GLMMs because it's such an important family.
Okay, thank you, Gareth.
I'll just add, can I just add one quick thing? Is I guess the thing where we could hope to do something is Metropolis within Gibbs samplers, where basically you replace exact Gibbs update with conditional invariance updates, and then what we would like to do, although it's not yet done, is to do some comparison argument and saying that to compare the convergence of the Metropolis within Gibbs, which you can implement, with the one of the idealized Gibbs, which you cannot implement. We're using ideas related to conditional capacitance to try to do that, but it's something which is very much preliminary at the moment. But methodologically wise, what you could just use is Metropolis within Gibbs samplers, and our theory doesn't apply there, but I would expect the guidance to, in a sense, be useful even there.